the tangent line problem. We begin our study of derivatives with a motivating problem involving the graph of a function. Differential calculus is motivated by the problem of finding a tangent line to the graph of a function f. Thanks in advance for watching this video. If you liked this video, don't forget to like and subscribe to this channel and activate the bell. It's very important for the continuity of this channel. We begin our study of derivatives by revisiting the notion of secant lines and tangent lines. A secant line of a curve is a straight line cutting a curve at 2 points. Look at the graph. A tangent line is a straight line which touches a curve at a point. Look at the graph. In elementary algebra, you have learned the concept of slope of a line. The slope of a line, also known as gradient, is a number which measures how steep is the line. For a non-vertical line, its slope or gradient is given by the denominator is the change in x, and the numerator is the change in y. For the sake of simplicity, the gradient or slope is denoted by the letter m. We need 2 points to compute the slope. So we can calculate the slope of the secant line by choosing 2 distinct points on the secant line. We can rewrite the gradient of secant line using the function notation. Now, suppose we want to find the slope of the tangent line at some specific point on the curve. Suppose we want to find the slope of the tangent line at point A. If we let the point B moves along the curve, the slope of secant line changes. So, if point B approaches point A along the curve, the corresponding secant line rotates about point A. And we expect the secant line to approach the tangent line. Therefore, the slope of the tangent line is the limit of the slope of the secant line as x approaches A. Because this type of limit occurs so widely, it is given a special name and notation, the derivative. We can summarize the discussion as follows. The slope of the tangent at x equals a is defined as the slope of the curve at the point where x equals a, and is the instantaneous rate of change in y with respect to x at that point. The slope of the tangent line at x equals a is called the derivative of function f of x at x equals a. The derivative of a function f of x at a number a is denoted by f prime a and is read as f dash of a or f prime of a. Finding the derivative of a function using this approach is referred to as finding the derivative of f from first principles. Let's see how it works. Find the derivative of f at x equals 2 using first principles. First, we apply the definition of derivative. Then we replace f with 2 times x squared plus 3. And a with 2. We factor out and expand terms. We simplify and replace x with 2. The tangent line to the graph is shown in figure below. There is another expression for the slope of a tangent line that is sometimes easier to use. If the distance between x and a is h, we can let h equals to x minus a. You should notice that as x approaches a, h approaches 0. So, alternatively, we may also define the derivative of a function as follows. Let's see another example. First, we write down the formula for finding the derivative, but now we use the alternative formula for finding the derivative. Then we replace a with minus 1 and we expand the numerator. Simplify the numerator. Factor the numerator. Cancel the common factor. And evaluate the limit. The tangent line to the graph is shown in the figure on the side. Before you learn how to find an equation of the tangent line to a curve at a given point, let's remember how is the point-slope form of the equation of a line. The point-slope equation of a line with slope m is given by. But we know that the derivative is the slope of the tangent line to the graph of f of x at the point a, f of a. So we can use the point-slope form of the equation of a line to write an equation of the tangent line to the curve y equals f of x at a specific point on the curve. The equation of the tangent line to the curve y equals f of x at the point a, f of a is given by the expression. Let's see how it works. First, we will find the point on the curve that the tangent line will pass through. We calculate f of 3. f of 3 is equal to 6. Then the tangent line passes the point 3 and 6. We now find the derivative at this point. We now use the equation of the tangent line to the curve f of x with the slope m is equal to 6 and the point 3 and 6. Let's see another example. First, we will find the point on the curve that the tangent line will pass through. We calculate f of 2. We now find the derivative at this point. We now use the equation of the tangent line to the curve f of x with the slope m equals 4 and the point 2 and 5.